composer that was famous for applying mathematical models in his compositions was Greek-French composer Yannis Xenakis, who was born in 1922 and died in 2001. Xenakis studied civil engineering and mathematics and worked at the cabinet of Le Corbusier, one of the most influential architects of the 20th century, before dedicating himself to composing. In his music, Xenakis applied several mathematical theories, mostly probabilistic, in order to write music that would have been impossible to imagine and to create otherwise, especially for his time. We're now going to take a closer look at one of the mathematical theories applied most in his work, the so-called sieve theory. Xenakis developed sieve theory during his stay in Berlin, having received a Ford Foundation grant to live and work in West Germany in 1963. The theory mainly concerns the creation of non-octaviantic scales, meaning scales whose pattern does not repeat itself after one octave, as do major, minor, or modal scales. The primordial sieve in mathematics is known as the sieve of Eratosthenes. The importance of this technique to Xenakis is fundamental. It has provided him with a method for filtering elements in order to create and manipulate structures. Furthermore, Xenakis' and Eratosthenes' methods share a common origin in the foundations of arithmetic. The sieve of Eratosthenes is a method for determining the prime numbers up to a given integer n. It is based on the following simple procedure. We write down in a matrix, in ascending order, all the integers from 2 to n. We leave the first element 2 and erase all its multiples. We leave the next number that has not been erased, 3, and erase all its multiples, and so on. We proceed until we reach prime number p. The remaining integers are the prime numbers between 2 and n. In our example, n is 50. The table consists of 4 parts, each for one stage of the process, and shows the crossouts for each element. In the top left part of the table, we have erased all the multiples of 2, every second number. In the top right part, all the multiples of 3, every third number, and so on for 5 and finally 7. More specifically, the first stage of the procedure starts at 2 and proceeds by steps of 2. The second stage starts at 3 and proceeds by steps of 3. The third at 5 and proceeds by 5. And the fourth at 7 and proceeds by 7. Some steps of one stage coincide with steps of another stage. This is shown as double or triple crossouts. Afterwards, only the starting points of these 4 stages are allowed through the sieve, that is 2, 3, 5, and 7. These elements are then added to the set of numbers greater than 7 that have not been erased, and the resulting set is the set of primes up to 50. These are the numbers of the bottom right part of the table that have not been erased. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and 47. What Xenakis drew from this is not merely the idea of filtering, passing the elements of a set through a sieve, but also the process of using starting points and steps of a specific distance. However, Xenakis' application of sieve theory is not intended to determine primes. His sieves allow both the starting points and all the following steps. The degree of complexity is a matter of compositional decision and aesthetics. This was done in a period where he would attempt to take further his investigation towards formalization. This time, though not with stochastic and probabilities, but with the aid of the deterministic laws that govern number and set theory. As he himself said, a sieve refers to a selection of points on a straight line. This is the abstract image of sieves. Every well-ordered set can be represented as points on a line if it is given a reference point for the origin and the length for the unit distance, and this is a sieve. The theory was used in order to construct symmetries at a desired degree of complexity. This was achieved by the combination of two or more modules. A module is notated by an ordered pair, M and R, that indicates a modulus, period, and a residue, an integer between 0 and m minus 1, within that modulus. For example, for m equals 3 and r equals 1, we have the following module. Elements that lie in distance equal to the value of the modulus are said to be congruent modulo m. In other words, elements that yield the same residue when divided by the same number belong to the same congruence class. In the examples, elements 4, 7, and 10 are congruent modulo. Let us apply this logic on musical pitches. Let's imagine that we want to filter out a musical scale based on the piano notes, the chromatic scale. Let's construct a 3.0 module starting from a C2, the lowest note of a cello. The number 0 shows that we are starting from the first note of the group we want to filter out, in this case the chromatic scale. If we wanted to start at C sharp 2, we would write it 3, 1. All the notes of our resulting 3, 0 module will be 3 semitones apart, meaning a minor third. The resulting scale would be the following, basically a diminished chord arpeggio. Let's now build another sieve, starting at the same C2 with the intention of filtering out the chromatic scale once again, this time building a 4-0 module, meaning a scale where all the notes are 4 semitones apart, meaning a major third. The result would be the following. Musically speaking, this would create an augmented chord arpeggio. For the next sieve, starting once again at C2, we will build a 5-0 module where all the notes are a perfect fourth apart from each other. The result is the following. In and of themselves, these sieves are not musically interesting, nor do we need mathematics to build them. But by applying the set theoretical operations of union, intersection, and complementation, or a combination of those three, one can construct more complex sieves musically interesting. The union of two modules is the binary operation that includes all of the elements that originally belong to both modules. For example, the union of modules 3, 0, and 4, 0 is 3, 0 plus 4, 0 equals 0, 3, 4, 6, 8, 9, 12, 15, 16, 18, 20, 21, 24, and so on and so forth. The period of this sieve is equal to the lowest common multiple, LCM, of 3 and 4, that is 12. The intervallic structure of a set is a listing of all its successive intervals. 3, 1, 2, 2, 1, 3, 3, 1, 2, 2, 1, 3. This type of structure is called symmetric, since the first part of the period is the mirror image of the second part. Sieves can be symmetric or asymmetric. In this particular case, since the set repeats itself after element 12, or in other words, its intervallic structure repeats after 12 units, meaning semitones, it is enough to represent it by only one occurrence of its period, like this. The union of the two modules, 3, 0 and 4, 0, would be the following. The union of the two modules 3, 0 and 5, 0 would be the following. The period would be the lowest common multiple of 3 and 5, that is 15, meaning that the period repeats itself after 15 semitones. The union of the two modules 4, 0 and 5, 0 would be the following. The period would be the lowest common multiple of 4 and 5, that is 20, meaning that the succession of intervals would be the same after 20 semitones. The union of all three modules, 3, 0, 4, 0, and 5, 0, is the following. This is the sieve that we are going to use from now on as a reference. Intersection refers to the coincidences or to the common elements of two modules. The intersection of the two modules 3, 0 and 4, 0 would be the following. The intersection of the two modules 3, 0 and 5, 0 would be the following. And the intersection of the two modules 4, 0 and 5, 0 would be the following. Complementation refers to the elements from the initial ensemble of elements that do not belong to any of the created modules. Since our initial ensemble was the chromatic scale of the piano, we're talking about all the notes that do not belong to any of the three modules we just showed. The result would be the following. Complementary sieves can also be used for musical and compositional purposes, and Xenakis himself has done so plenty of times. Decomposing the period is not possible for all sieves. Factorial decomposability refers to intersections of modules and depends on whether the period of the sieve is a prime or a composite number. It follows that sieves whose period is prime cannot be decomposed into factors and therefore cannot be notated except according to the period only. Of course, a prime period can be found in any sieve, either symmetric or asymmetric. A prime asymmetric sieve is the one used in Xenakis' work Jonché for orchestra, written in 1977. Its intervallic structure is asymmetric, and its period is 1 octave and a perfect fourth, that is 17 semitones, which is a prime. This type of sieves can be notated according to their period only, which is equivalent to writing down all its pitch classes. In this case, 0, 1, 4, 5, 7, 11, 12, 16. In other words, the sieve of Jonché can be written only as a union of 8 modules, one of each element of one period of the scale. Let's share modulus 17, where 0 is A2. Let us now listen to the beginning of this work to get an idea of what a sieve can sound like musically. Another operation one can apply on a given sieve is the inversion. The inversion, in the case of a sieve, would be to start at the top note of the given ensemble and to apply the same succession of intervals, but this time downwards. In our case, our top note is, arbitrarily, the G7 that we can see in the complementary sieve. Starting from the G7 and applying the same succession of intervals downwards, we have the following sieve. And it's complementary. Up until now, all the modules we have looked at, they all shared the same starting point, 0. In our case, C2. But the modules do not have to start at the same point. Let us now look at modules 4.1 and 5.2, all applied to our chromatic scale between C2 and G7. Module 4.1 starts at C-sharp 2, and its notes are all a major third apart as before. And module 5.2 starts at D2, and its notes are all a perfect fourth apart as before. As an exercise, I invite you now to write down the unions and the intersections of all the modules. 3.0 plus 4.1, 3.0 plus 5.2, 4.1 plus 5.2, and 3.0, 4.1, and 5.2, along with a complementary sieve of this last one. After you are done with the union of these three modules and its complementary sieve, write the inversion of the two sieves. Starting at the top note of the sieve, G7, keep the same intervals but moving downwards.